Welcome to Between Sleep and Science, a place where the boundaries of the mundane world begin to dissolve and the vast silent reaches of the cosmos come into focus. Tonight, we step away from the relentless noise of the world, leaving behind the frantic pace of our daily lives, the ticking of the deadline, and the pressure of the immediate. We are here to contemplate the most profound enigma in the history of the universe, time itself. It is the invisible current that carries our lives, the silent architect of our destiny, and the medium in which every action we take is inscribed. Yet, despite its omnipresence, we find it almost impossible to truly define. St. Augustine once famously remarked that he knew what time was until someone asked him to explain it. This sentiment has echoed through the millennia as the greatest minds of humanity have stood on the shores of this mystery, looking out at an ocean that seems to have no beginning and no end. We feel the weight of time in every passing season, in every fading memory, and in every beat of our hearts. It is the measure of our growth and the herald of our aging, but the moment we try to grasp its essence, it slips through our fingers like stardust, leaving us with more questions than answers. Is time a fundamental property of the universe, or is it merely a construct of the human mind? A tool we developed to organize our sensory experiences? This question leads us to the heart of a debate that has lasted for centuries. On one side, we have the presentists, who believe that only the present moment is real. To them, the past is a ghost and the future is a void. On the other side, we have the eternalists, who argue that time is a fourth dimension as real as the three dimensions of space. In the realm of modern physics, the eternalist view has gained significant ground through the concept of the block universe. This theory suggests that the past, present, and future all exist simultaneously, laid out like a giant four-dimensional landscape. Imagine the universe as a solid block of crystal. Inside this block, every event that has ever happened and every event that will ever happen is frozen in its specific coordinates. In this view, our perception of a moving now is simply an illusion created by our consciousness as it traverses this landscape. Every moment you have ever lived, every laugh, every tear, and every breath is already there, etched permanently into the fabric of space-time. Your childhood is not gone. It is simply located at a different set of coordinates in the block. Why, then, does time seem to move? Why do we perceive a flow? This psychological elasticity is one of the greatest mysteries of consciousness. We know that time seems to move at a crawl when we are in pain or waiting in boredom, and yet it flies like a bird when we are lost in the ecstasy of joy or the deep focus of a creative task. Our brains do not have a single clock sensor. Instead, we perceive time through the accumulation of memories and the processing of sensory data. When we are young and every experience is new, our brains record more information, making time feel long in retrospect. As we age and life becomes more predictable, our brains summarize our experiences, and the years seem to vanish in an instant. Throughout history, philosophers like Immanuel Kant and Martin Heidegger have tried to bridge the gap between the objective time of the universe and the subjective time of the soul. Kant argued that time is an a priori intuition, a lens through which we must perceive the world rather than a thing that exists outside of us. Heidegger, in his masterpiece, Being and Time, argued that our very existence is defined by our relationship with time and the inevitable horizon of our own mortality. To be human is to be temporal. Tonight, we will navigate the staggering revelations of relativity, peer into the deep, light-swallowing shadows of black holes, and wonder at the strange mathematical symmetry of the cosmos. We will ask why time has an arrow, why we can remember the past but not the future. We will explore space-time, a word that forces us to realize that where and when are two sides of the same coin. We will look at how the speed of light sets the pace of the universe and how gravity itself can stretch a second into an eternity. As we begin this quiet exploration, I invite you to simply settle in. Adjust your surroundings until you find a state of total comfort. Feel the support of the surface beneath you and let your breathing find its natural, effortless rhythm. Let the distractions of the day, the worries, the plans, the echoes of conversations fade into the background like a distant radio station being tuned out. Allow the gentle, rhythmic flow of these cosmic truths to carry you toward a state of profound rest. One sleepy soul at a time, we will uncover why the universe keeps its clock the way it does. We will journey through the history of light, the violent birth of stars, and the inevitable silent end of everything. Let us begin our journey into the fourth dimension, where the secrets of reality await. 2. The illusion of the universal clock, a history of measurement and mastery. To our limited human senses, time feels like an unwavering companion, a silent witness to our lives that never falters. It seems to tick forward with a perfect, icy regularity, indifferent to our desires or our despairs. Whether we are lost in the vivid landscapes of a dream or busy with the crushing demands of a hectic day, we perceive each second as identical to the last. This is our biological baseline, the rhythm of our nervous system. For most of human history, we believed this rhythm was universal. We assumed that the sun rose and set for everyone at the same pace, and that a year in one land was exactly a year in another. We saw time as a giant celestial clockwork set in motion by a divine hand. We have spent thousands of years building tools to capture and quantify this rhythm. Our ancestors began with the heavens, turning their gaze upward to find a sense of order in the chaos. They watched the phases of the moon and the movements of the planets, linking their survival, the planting of crops, the migration of herds, to the celestial cycles. The first sundials were simple sticks in the sand, translating the rotation of the earth into the movement of a shadow. These shadow clocks were our first attempt to tether time to the physical world. In ancient Egypt, massive obelisks served as public timekeepers, their long shadows marking the passage of the day for an entire city. But sundials were useless at night or under a cloudy sky. The need for continuous timekeeping led to the invention of water clocks, or clepsydre. These devices measured the steady drip of liquid from one vessel to another, often using a floating marker to indicate the hour. In ancient Greece and China, water clocks became incredibly sophisticated, sometimes featuring complex mechanical systems that could track the seasons or the positions of the stars. Later, sand-filled hourglasses provided a portable and reliable way to measure duration, especially on ships where water clocks would be affected by the rocking of the sea. Each of these inventions was a mimicry, an attempt to use the predictable flow of matter to represent the invisible flow of moments. The true revolution came in the 13th and 14th centuries with the invention of the mechanical clock. This was a turning point in human consciousness. For the first time, time was not measured by the flow of nature, but by the precise mechanical interaction of gears and escapements. The invention of the escapement, a mechanism that releases energy in discrete ticks, allowed for the creation of clocks that were independent of the sun and the stars. The clock tower became the heart of the European city, synchronizing the prayers of monks, the opening of markets, and the shifts of workers. Time became a commodity, something that could be spent, saved, or wasted. We moved from organic time to mechanical time, a shift that paved the way for the Industrial Revolution. By the 18th century, the challenge of navigation led to one of the most important scientific quests in history. Sailors could calculate their latitude by the stars, but calculating longitude required knowing the exact time at a home port. On a long voyage, a standard mechanical clock would lose minutes due to changes in temperature and the motion of the ship, leading to shipwrecks and lost fortunes. This led the British government to offer the Longitude Prize. A self-taught clockmaker named John Harrison spent decades perfecting the marine chronometer. His fourth version, the H4, was a masterpiece of engineering that could keep time to within a few seconds after months at sea. Harrison's work transformed the world, enabling the age of global exploration and trade. Today, we have moved far beyond gears and springs. In the early 20th century, we discovered that certain crystals, like quartz, vibrate at an incredibly stable frequency when an electric current is applied. This led to the creation of quartz clocks, which are far more accurate than any mechanical device. But even quartz was not enough for the needs of modern science and technology. In the 1950s, we developed the first atomic clocks. These devices do not rely on macroscopic vibrations, but on the hyperfine transitions of electrons in atoms, usually cesium-133. According to the International System of Units, a second is now defined as the duration of exactly 9,192,631,770 periods of the radiation, corresponding to the transition between two levels of the ground state of the cesium atom. These atomic devices are so accurate, they will not lose a single second in hundreds of millions of years. We trust them to synchronize global telecommunications, manage power grids, and conduct high-speed financial trades where a millisecond can mean millions of dollars. We move through our days assuming that time is a rigid, objective background, an absolute value that is the same for a person in London as it is for an explorer in the Antarctic. We assume that if we synchronize two of these perfect clocks and send one to the other side of the world, they will still show the same time when they return. But this perceived regularity is, in fact, a grand illusion. It is a product of our specific, low-energy environment. We live at slow speeds on a planet with relatively weak gravity. Because our experience is confined to this slow corner of the universe, our intuition lies to us. We think time is a river, but it is more like a sea that can be disturbed by waves of mass and motion. Beneath the surface of our daily lives lies a deeper, more fluid truth. Time is not a universal river that carries all things at the same speed. It is not a passive stage upon which the universe acts. Instead, time is a participant in the physical drama. It is malleable, shaped by the unseen hands of gravity and the sheer velocity of motion. It is as if the universe is made of a material that can be squeezed and pulled, affecting the rate at which events unfold. What we perceive as a fixed rhythm is, in reality, a deeply personal experience, a proper time that belongs to your specific path through the cosmos. Your now is not necessarily the same as the now of an observer on a distant galaxy. We are all moving through time at different rates, and the only reason we don't notice it is that we are all huddled together on the same slow-moving rock. Tonight, we break free from that rock and look at the universe as it truly is, a place where the clock is never the same for everyone, and where the very fabric of reality is woven from the threads of time. Third, the relativistic revolution, Einstein's 1905 breakthrough, and the death of absolute time. For over 200 years, the scientific world was governed by the majestic intuition of Isaac Newton. In his monumental work, Philosophia Naturalis Principia Mathematica, Newton laid out the laws of motion and universal gravitation that defined the Enlightenment and the scientific revolution. To Newton, space was an infinite, empty container, and time was an absolute mathematical flow that proceeded without relation to anything external. In the Newtonian universe, time was the independent variable, a rigid backdrop against which all physical events occurred. If you could place a perfect clock in the center of the galaxy, it would report the exact same time as a clock on Earth. This view was so successful that it became the foundation of modern engineering, astronomy, and physics. It felt correct because it perfectly matched every observation made by the human eye and every experiment conducted with macroscopic objects. However, toward the end of the 19th century, a deep crisis began to brew in the heart of physics. Scientists were studying electromagnetism and the nature of light, led by the equations of James Clerk Maxwell. Maxwell's equations suggested that light was an electromagnetic wave that traveled at a specific speed, roughly 300,000 kilometers per second. This raised a fundamental question: speed relative to what? At the time, physicists assumed that light must travel through a medium, just as sound travels through air, or waves travel through water. They called this hypothetical medium the luminiferous ether. This led to the famous Michelson-Morley experiment in 1887. Albert Michelson and Edward Morley designed an incredibly sensitive instrument called an interferometer to detect the Earth's motion through the ether as it orbited the Sun. They expected to find that the speed of light varied depending on whether it was moving with the Earth's ether wind or against it. But to their shock, they found nothing. The speed of light remained stubbornly constant in every direction. The ether didn't exist, and the Newtonian addition of velocities didn't work for light. If you are on a train moving at 50 miles per hour and throw a ball forward at 10 miles per hour, someone on the ground sees the ball moving at 60. But if you shine a flashlight forward, everyone sees the light moving at exactly the same speed, regardless of how fast the train is going. Enter Albert Einstein. In 1905, while working as a low-level technical expert Class 3 in the Swiss Patent Office in Bern, Einstein published a series of papers that would shatter our traditional understanding of existence. He wasn't a famous professor. He was a 26-year-old outsider who spent his days evaluating patent applications for telegraphs and synchronized clocks. Perhaps it was his daily focus on the synchronization of distant clocks, a major industrial challenge of the time, that led him to his breakthrough. Einstein realized that if the speed of light is indeed constant for all observers, then our traditional concepts of space and time must be the variables that give way. Einstein proposed two simple but revolutionary postulates that form the basis of the special theory of relativity. First, the laws of physics are the same for everyone in uniform motion. Second, the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the source. From these premises, Einstein derived a set of equations that redefined the universe. He showed that time is not a separate, absolute entity. Instead, it is inextricably woven with the three dimensions of space, length, width, and height, into a single, four-dimensional fabric called space-time. Imagine a vast, flexible mesh that covers the entire universe. Every event in history has a specific address in this mesh, defined by 3 coordinates in space and 1 in time. Einstein realized that as you move through space, your experience of time must change to keep the speed of light constant. There is a fundamental trade-off between these dimensions. If you are sitting perfectly still, all of your motion is directed through the dimension of time. But as you begin to move through space, some of that temporal motion is redirected. The faster you move through space, the slower you move through time. This is why time dilation occurs. This wasn't merely a philosophical debate. It was a radical redefinition of reality. Einstein was telling us that the universe has an absolute speed limit, and that time is the elastic variable that preserves the logic of the cosmos. What feels like a fleeting hour to a traveler racing near the speed of light could equate to decades for someone remaining still on Earth. Einstein used Gedanken experiments to prove this. He imagined a clock made of 2 mirrors and a bouncing beam of light. For someone riding with the clock, the light bounces straight up and down. Но для наблюдателя, мимо которого этот световой хронометр пролетает на огромной скорости, путь света выглядит как длинная зигзагообразная линия. Поскольку свет должен преодолеть большее расстояние с той же скоростью, время для движущегося объекта обязано идти медленнее. The beauty of special relativity lies in the Lorentz transformation, the mathematical bridge that allows us to translate measurements between different frames of reference. It introduced the world to the idea that simultaneity is relative. 2 events that happen at the same time for one person might happen at different times for someone else. There is no universal now that covers the whole universe. Every experiment conducted in the last century has confirmed this strange and beautiful reality. We have tracked subatomic particles called muons that travel so fast their internal clocks slow down, allowing them to reach the Earth's surface before they decay. We have sent atomic clocks around the world on jet planes and found that they lose billionths of a second compared to clocks on the ground. Time is not the steady, mechanical metronome of our ancestors. It is an ethereal, living dimension that adapts to the movement and perspective of the observer. Einstein's vision didn't just change physics, It changed how we perceive our place in the flow of existence. We are not just living in time, we are moving through it, and our speed determines the very rhythm of our lives. 4. The speed of light, the universe's absolute limit and the fabric of causality. At the heart of Einstein's revolutionary equations, and at the foundation of the universe itself, sits a single sacred number, the speed of light. In the cold, perfect vacuum of space, light travels at exactly 299,792,458 meters per second. This number, represented by the letter C in physics, is not just an impressive speed. It is the ultimate speed limit of the cosmos. It is the speed of causality itself, the maximum rate at which any information, signal, or influence can travel from one point to another. If something happens on the other side of the room, you cannot know about it until the light or the sound, which is much slower, reaches you. In the vacuum of space, light is the fastest messenger, and its speed determines the structure of everything we perceive. One of the most counterintuitive aspects of relativity is that no object with mass can ever reach this velocity. To understand why, we must look at Einstein's most famous equation, E equals mc squared. This formula, often cited but rarely understood in its full depth, tells us that energy and mass are two sides of the same coin. Mass is essentially highly concentrated energy. As an object accelerates, you are adding kinetic energy to it. At everyday speeds, this just makes the object go faster. But as you approach the speed of light, that energy begins to manifest in a different way, as an increase in relativistic mass or inertia. The object becomes heavier and harder to push. Imagine a proton being accelerated in the Large Hadron Collider at CERN. As it reaches 99.99% of the speed of light, adding more energy doesn't significantly increase its speed. Instead, the energy makes the proton more massive, requiring even more power to produce a tiny gain in velocity. To reach the speed of light, an object would require an infinite amount of energy, which would mean it would have to possess more energy than exists in the entire universe. Thus, light speed is a barrier that can be approached but never touched by anything made of matter. Only massless particles like photons, particles of light, or gluons can travel at this speed, and they must travel at this speed. They have no choice. They are born moving at c. But why does this limit exist? Why is the universe structured this way? The speed of light is not just a limit for things moving through space. It is a fundamental property of the geometry of space-time. In a four-dimensional universe, the total speed of any object through space-time is always exactly equal to c. If you are sitting perfectly still in space, all of your speed is directed through the dimension of time. As you begin to move through space, you must borrow some of that speed from the time dimension. If you were to reach the speed of light through space, you would have zero speed left for the time dimension. Time would stop. The constancy of the speed of light, the fact that it is identical for all observers regardless of their motion, is the most profound anchor of our reality. In our everyday experience, if you are driving a car at 50 miles per hour and another car passes you at 60 miles per hour, you see that car moving at 10 miles per hour relative to you. Velocities add or subtract according to the Galilean transformation. But light does not play by these rules. If you are standing still on a planet, you measure a beam of light passing you at 300,000 kilometers per second. If you board a rocket ship moving at 90% the speed of light and measure that same beam, it will still pass you at exactly 300,000 kilometers per second relative to you. This constancy seems to defy every rule of common sense. How can light move at the same speed relative to two people moving at vastly different velocities? The answer lies in the flexibility of time and space. Since speed is defined as distance divided by time, and the speed of light must remain constant, then distance and time must be the variables that give way. Space contracts, length contraction, and time slows down, time dilation. Time is not a rigid ruler. It is a shock absorber that compresses and stretches to keep the fundamental constant of the universe intact. We exist in a world where time sacrifices its stability so that light can remain unchanging. This is the cornerstone of our reality. The speed of light is the tether that holds the universe together. It defines the structure of space-time and sets the limits of what we can know and where we can go. It is the cosmic speed limit that ensures causes always happen before their effects, protecting the logical structure of history itself. If anything could travel faster than light, it could, according to relativity, travel backward in time relative to some observers. This would create causality paradoxes that would tear the fabric of logic apart. The speed of light is the guardian of causality, the heartbeat of the cosmos. It is the reason the universe makes sense. V. Looking into the ghost of the past. Light as a time machine and the cosmic archive. When you step outside on a clear morning and feel the warmth of the sun on your face, you are touching history. You are not feeling the sun as it exists in this very moment. You are feeling the sun as it was 8 minutes and 20 seconds ago. That is the time it takes for light to cross the 150 million kilometer gulf between our star and our planet. Every particle of light or photon that touches your skin has made a long and lonely journey through the vacuum of space, carrying within it information about the sun's past. We are always looking at the sun's ghost, unaware of what it is doing right now until the future light arrives. This delay is a profound reminder that looking across distance is a form of time travel. Because light takes time to travel, we never see the universe in real time. We see a layered history, where the further we look, the deeper we peer into the past. If the sun were to suddenly vanish from existence this very instant, we would continue to see its light and feel its gravity for over 8 minutes. For that duration, we would live in a world whose source of life was already gone, floating through a bright sky that was already a memory. We are always living in the past tense of the cosmos. This effect scales with distance, becoming increasingly breathtaking as we look further into the dark. The light from the moon is a mere second delay. We see it as it was a heartbeat ago. When we look at Mars, we see it as it was 3 to 20 minutes ago, depending on its position in its orbit. But once we leave our solar system, the scales become truly astronomical. The nearest star beyond our Sun, Proxima Centauri, is seen by us as it was over 4 years ago. We see not its current self, but its state when the light began its journey across the 4 light-year void. If a massive solar flare erupted on Proxima Centauri today, We wouldn't know about it until 4 years from now. When we look at the Andromeda Galaxy with the naked eye, a faint smudge of light in the autumn sky, we are seeing light that left its source 2.5 million years ago. That light began its journey long before modern humans walked the Earth, back when our ancestors were just beginning to use simple stone tools. We are seeing a galaxy as it existed in a time that is ancient beyond human comprehension. The stars we see in that smudge may have long since exploded or evolved, but their image is only now reaching our shores. When we point our most powerful telescopes, like the James Webb or the Hubble, at the most distant galaxies, the numbers become truly staggering. We are looking back billions of years. We see galaxies as they were when the universe was in its extreme youth, shortly after the Big Bang. We see starburst galaxies, where stars are being born at a furious rate. And we see quasars powered by massive black holes that have long since grown quiet. We see stars that have long since burned out and exploded, their light only now reaching our eyes. Every glance at the night sky is an archival journey through the history of light. We are surrounded by the shadows of the past, and in this sense, the night sky is the largest library in existence. This delay also sets a fundamental limit on our ability to communicate with the rest of the universe. If we were to send a radio signal to a potential civilization on a planet orbiting a star 50 light-years away, it would take 50 years to arrive. Even if they replied immediately, we wouldn't receive their answer for another 50 years. A simple hello would take a century to complete. This light time creates a natural isolation in the universe, turning every star system into a temporal island. We are connected by light, but we are separated by time. The speed of light is the maximum speed of a conversation. Understanding this changes how we perceive the stars. They are not just points of light, they are signals from different eras. Some of the stars you see tonight might not even exist anymore, while others that have already formed haven't had their light reach us yet. We are witnesses to a cosmic playback, watching a movie that has been filming for 13.8 billion years. Every photon is a messenger from history, carrying the secrets of the early universe across the eons. We are the inheritors of this light, the observers who give meaning to the long-dead fires of the past. To study the stars is to study our own ancestry, written in the light of distant suns. 6. Time. Dilation. The science of stretching moments and the twin paradox. To truly understand how motion affects time, we must look at the phenomenon of time dilation. This is not just a theoretical equation scribbled on a chalkboard or a clever trick of the mind. It is a physical reality that has been tested with staggering precision in laboratories and in orbit. Imagine you are a traveler on a spacecraft capable of reaching 99.9% of the speed of light. You leave Earth and accelerate into the dark. Inside your ship, everything feels normal. Your heart beats at its usual rate. Your thoughts flow naturally, and your clock ticks with a familiar rhythm. You do not feel slow. You feel like yourself. You could read a book, have a meal, and sleep, and your perception of a second would remain unchanged. However, to an observer on Earth watching you through an impossibly powerful telescope, your life would appear to be frozen in molasses. Every movement you made, every second that passed on your clock would seem stretched out. if you were to wave your hand, it would take years for the earthbound observer to see that gesture completed. This is not an optical illusion caused by distance, nor is it a signal delay. It is a physical change in the structure of time. Your motion through space is eating your motion through time. According to the Lorentz transformation equations, as your velocity approaches c, the time interval between two events in your frame of reference expands from the perspective of a stationary observer. The consequences are staggering and lead to what physicists call the twin paradox. Imagine two identical twins. One boards a high-speed spacecraft to a distant star system, while the other stays on Earth. The traveling twin journeys at near light speed for what feels to them like 5 years. They visit a star, conduct their research, and return. When they land on Earth, they find that they have effectively leaped into the future. Their twin who stayed behind might be elderly, and their friends might be long gone. The traveler has aged only 5 years, but the Earth has aged 50 or even 100 years. The traveling twin is now a historical relic in a future world. Is this really a paradox? Newton would say yes, but Einstein says no. The symmetry is broken because the traveling twin had to accelerate, turn around and decelerate, which means they changed their frame of reference. The stay-at-home twin remained in a single inertial frame. This asymmetry means the traveler really did experience less time. This is not just a thought experiment. We see this effect every day in the subatomic world. Particles called muons are created in the upper atmosphere by cosmic rays striking air molecules. Muons are unstable and have a very short lifespan, about 2.2 microseconds, before they decay into other particles. Even traveling near the speed of light, they shouldn't have enough time to reach the ground before they vanish. And yet, we detect them in great numbers at sea level. The reason is time dilation. Because the muons are moving so fast relative to us, their internal clocks slow down. For the muon, only 2 microseconds pass. But for us, those 2 microseconds are stretched long enough for them to complete their 15-kilometer journey to the ground. At the theoretical limit, the speed of light itself, time stops entirely. This is why photons do not age. From a photon's perspective, its emission from a distant star and its absorption by your eye happen at the exact same instant, regardless of the billions of years that pass for us. For light, the universe has no duration. It exists in a state of eternal now. This stretching of moments is a fundamental feature of our universe. It shows us that time is not a fixed background, but a dynamic property of our path through space-time. We are all moving at the speed of light through the 4-dimensional block of reality. It's just a question of how much of that speed is through space and how much is through time. Time dilation is the universe's way of ensuring that no matter how fast you go, you can never break the speed of light. Time will simply slow down to accommodate you. It is a profound, built-in protection for the logic of the cosmos. 7. Relativity in the modern world. GPS, atomic clocks, and daily dilation. These concepts might sound like science fiction or abstract philosophy, but they are absolutely essential for the technology you use every single second of your day. You don't need a warp drive or a journey to a distant star to observe time dilation. We see it in our satellites. Astronauts aboard the International Space Station orbit Earth at roughly 28,000 kilometers per hour. While this is only a tiny fraction of light speed, It is enough to cause their clocks to drift relative to ours. Because they are moving faster than people on the ground, their time slows down slightly due to special relativity. However, there is a second, even more powerful effect at play. According to Einstein's general theory of relativity, gravity also affects time. Since the satellites are further from Earth's mass, gravity is weaker there, which causes time to go faster. These two effects, speed and gravity, are constantly fighting each other. For the GPS satellites, which orbit much higher, about 20,000 kilometers, than the ISS, the speeding up effect of weak gravity is much stronger than the slowing down effect of motion. The net result is that the atomic clocks on GPS satellites tick ahead of clocks on the ground by about 38 microseconds per day. This might seem like a negligible amount of time, 38 millionths of a second. But light, and the radio signals from GPS, travels 300 meters in a single microsecond. If the engineers at the Department of Defense did not account for Einstein's theories of relativity, the timing errors would accumulate. Within just one day, your GPS position on a map would be off by about 10 kilometers. Within a week, the entire global navigation system would be completely useless. Every time your phone pinpoints your location to within a few meters, it is effectively solving the complex equations of relativity in the background. Modern civilization is literally built upon the realization that time is relative. We have tested these effects even more directly on Earth. In 1971, the Haferle-Keating experiment involved taking 4 cesium atomic clocks and flying them twice around the world on commercial jetliners, once eastward and once westward. When the clocks were brought back and compared to stationary clocks at the US Naval Observatory, the results were exactly what Einstein predicted. The clocks that traveled eastward, moving faster relative to the Earth's center, lost time, while the clocks that traveled westward, moving slower, gained time, adjusted for the gravitational effects of their altitude. Today, we use ultra-precise atomic clocks at research facilities like NIST, the National Institute of Standards and Technology. These clocks use the hyperfine transitions of atoms to measure time so accurately that they can detect the time difference between your head and your feet. Because your feet are closer to the center of the Earth, they are in a slightly stronger gravitational field, and thus age slightly slower than your head. Over a lifetime, the difference is only billionths of a second. Too small for you to feel, but our instruments are now sensitive enough to see it. This means that time is not a flat plane. It is a landscape of valleys and peaks. Gravity creates time wells. If you live in a deep valley, your life is unfolding slightly slower than the life of someone on a mountain peak. These experiments prove that relativity is not just a theory for the stars. It is a fundamental truth of our everyday environment. We are living in a world of shifting time flows, where every move we make and every height we climb changes our personal duration. We are all moving through time at our own unique pace, dictated by the mass beneath us and the speed of our journey. 8. Gravity, the curvature of space-time and the fabric of the cosmos. In 1915, 10 years after his first breakthrough, Einstein expanded his vision with the general theory of relativity. He realized that the special theory only applied to objects moving at a constant speed, inertial frames. But the real world is full of acceleration, rotation, and gravity. Newton had described gravity as an invisible force, an action at a distance, that pulled objects together across empty space. But Newton himself was troubled by this. He couldn't explain how gravity communicated its pull. Einstein provided the answer by reimagining the very geometry of the universe. Einstein realized that space and time are not just a stage, but a flexible, dynamic fabric. Imagine stretching out a large rubber sheet and placing a heavy bowling ball in the center. The ball creates a dip or a curve in the fabric. This is how mass affects space. If you then roll a smaller marble onto that sheet, it won't move in a straight line. It will follow the curve created by the bowling ball, perhaps even orbiting around it. This is gravity. It is not a force pulling on the marble. It is the marble following the natural curvature of the path it is on. In the words of physicist John Wheeler, matter tells space-time how to curve, and space-time tells matter how to move. But Einstein's great insight was that this curvature doesn't just affect space, it affects time. This is the equivalence principle. He imagined a person in an elevator. If the elevator is in deep space and accelerating upward, the person feels a pull toward the floor that is indistinguishable from gravity on Earth. If the person shone a flashlight across the elevator, the light would appear to bend toward the floor because the elevator moved upward while the light was in transit. If gravity and acceleration are the same, then gravity must also bend light. And if gravity bends light, it must be because gravity is curving the very space-time that light travels through. The stronger the gravitational field, the more space-time is stretched or warped, and the slower time flows. This is gravitational time dilation. Imagine two clocks, one sitting on the surface of a massive star and one floating in empty space. The clock on the star is deep in a gravitational well where space-time is highly curved. For every tick of that clock, the distant clock might tick twice. To an observer on the star, the distant universe appears to be moving in fast forward. To the distant observer, the clock on the star seems to be moving in slow motion. This has been proven countless times. In 1919, during a solar eclipse, Sir Arthur Eddington measured the positions of stars near the Sun. He found that their light was indeed bent by the Sun's mass, exactly as Einstein predicted. This discovery made Einstein a global celebrity overnight. More recently, the Gravity Probe B satellite confirmed frame dragging, the way a rotating mass like the Earth actually twists the space-time fabric around it, like a spoon spinning in honey. Gravity literally slows the aging of the universe itself near massive objects. This means that time is not just a measurement, it is a physical condition. If you were to spend a week on a planet orbiting very close to a massive star, you would return to find that much more time had passed in the rest of the galaxy. It reminds us that our experience of duration is entirely dependent on our proximity to mass. We are tethered to the Earth, not just by a force, but by a curvature that defines our very existence in time. We are living in a warp in the universe, and that warp is what gives us our sense of down and our rhythm of life. 9. The abyss, black holes, Schwarzschild and the singularity. To see the most extreme version of space-time warping, we must look to the most mysterious objects in the cosmos, black holes. The concept of a black hole began as a mathematical solution to Einstein's equations. In 1916, while serving on the front lines of World War I, the German physicist Karl Schwarzschild calculated what would happen if a mass was compressed into a sufficiently small region. He found that there was a critical radius, now called the Schwarzschild radius, where the curvature of space-time becomes infinite and the escape velocity exceeds the speed of light. Einstein himself was skeptical that such objects could actually exist in nature, but decades of astronomical observations have proven otherwise. A black hole is formed when a massive star exhausts its nuclear fuel and collapses under its own weight. The gravity becomes so intense that it overcomes every known force, crushing the star's matter into a single point of infinite density called a singularity. Here, the laws of physics as we know them break down. Space and time as we understand them come to an end. The boundary surrounding a black hole is called the event horizon. This is the point of no return. Once anything, even light, crosses this boundary, it is lost forever. Because nothing can escape, we cannot see the interior of a black hole. We can only see its shadow against the surrounding light. In 2019, the Event Horizon Telescope captured the first ever image of this shadow in the galaxy M87, a historic confirmation of Einstein's predictions. Near the event horizon, gravitational time dilation reaches its ultimate limit. If you were to watch a companion fall into a black hole from a safe distance, you would witness a haunting and paradoxical event. As your companion approached the horizon, you would see their movements become increasingly sluggish. As they reached the edge, their image would become redder and dimmer due to the extreme gravitational redshift, the light itself losing energy as it struggles to climb out of the gravitational well. To your eyes, your companion would eventually appear to stop completely, frozen in time at the very edge of the abyss. From your perspective, it would take an infinite amount of time for them to cross. However, from the perspective of the falling companion, the experience would be quite different. They would cross the horizon in a finite amount of time, perhaps even without noticing the exact moment they passed the point of no return. But as they looked back at the universe they were leaving, they would see time outside accelerating wildly. They would watch the stars in the galaxy burn through their lifespans, witness galaxies collide, and see the entire future of the universe unfold in a final, brilliant flash of light before they were drawn into the singularity. Inside a black hole, the structure of space-time is so distorted that time and space effectively swap roles. For us, movement into the future is inevitable, but we can choose where to go in space. Inside the horizon, movement toward the singularity becomes as inevitable as the passage of time. You cannot stand still or move away. The center is no longer a place, but a moment in your unavoidable future. Black holes also raise the information paradox. If information falls into a black hole and the black hole eventually evaporates, is that information lost? This conflict between general relativity and quantum mechanics is one of the biggest mysteries in physics today. Some, like Stephen Hawking and Leonard Susskind, have proposed the holographic principle, suggesting that the information is actually encoded on the two-dimensional surface of the event horizon. This implies that our three-dimensional world might be a projection of information stored on a distant boundary. Black holes are the ultimate expression of gravity's power over time, a dark frontier where the history of our universe ends and the deep mysteries of quantum gravity begin. X, the arrow of time, entropy, order, and the great mystery of direction. One of the most haunting and fundamental questions in all of physics is, why does time only flow in one direction? We experience a profound asymmetry in our lives. We remember the past, but we cannot remember the future. We see an egg break on the floor, but we never see the shards, and the yolk spontaneously jump back together to form a whole egg. We see people age, but never grow younger. This one-way street is known as the arrow of time. Curiously, when we look at the fundamental equations of physics, Newton's laws, Maxwell's equations of electromagnetism, or even the Schrödinger equation in quantum mechanics, they are mostly time-symmetric. They work just as well whether time moves forward or backward. If you film a collision of two billiard balls and play it in reverse, it still looks like a valid physical event. So why does the macroscopic world choose a single direction? Why is there a before and an after? The answer lies in the field of statistical mechanics and the concept of entropy, or disorder. The second law of thermodynamics states that in any isolated system, the total entropy will always increase over time. Entropy is a measure of the number of ways a system can be arranged. A whole egg is a highly ordered, low-entropy state. There is only one way to be a whole egg. A broken egg, however, is a state of high entropy, and there are millions of ways the pieces can be scattered on the floor. The reason time has an arrow is that the universe is constantly moving from a state of low entropy to a state of high entropy. This transition is not a law of force, but a law of probability. While it is theoretically possible for all the molecules of a broken egg to happen to vibrate in the exact way needed to reassemble it, the odds are so astronomically low that it would likely never happen in the lifespan of 1 trillion universes. Disorder is simply more probable than order. The ultimate source of the arrow of time is the Big Bang. Our universe began in a state of extremely low entropy, an unimaginably hot, dense, and ordered point. Since that initial moment, 13.8 billion years ago, the universe has been expanding and becoming more disordered. This march from order to chaos is what defines the passage of time as we perceive it. Every star that burns its nuclear fuel, every galaxy that drifts away, and every biological process in our bodies is a local contribution to the total increase in entropy. This increase in disorder is the reason for memory and causality. We can have a record of the past because the past was in a state of lower entropy, leaving traces like photographs, fossils, or neural patterns. The future, being more disordered, hasn't left these traces yet. We are living in the decay of the initial order of the Big Bang. Without the growth of entropy, there would be no distinction between yesterday and tomorrow. The universe would be a static, timeless equilibrium where nothing ever happens. The arrow of time is the signature of a universe that is evolving, a cosmic journey from a singular beginning toward an uncertain end. It is what gives our lives meaning, ensuring that every moment is unique and irreversible. We are travelers on a road that only goes one way, carried by the relentless tide of increasing entropy. 11. The Big Bang, the creation of space and time and the echoes of origin. If time has a direction and entropy is always increasing, then the universe must have had a definitive starting point, a moment of minimum entropy. Modern cosmology points to this moment as the Big Bang, which occurred approximately 13.8 billion years ago. It is a common misconception to think of the Big Bang as an explosion of matter into an empty, pre-existing space. In reality, it was the simultaneous creation of space and time themselves. The universe didn't expand into anything. The outside does not exist. Before the Big Bang, the concepts of before, where, and duration may not have existed at all. It was the moment the cosmic clock started ticking. The great physicist Stephen Hawking often compared this to asking, what is north of the North Pole? The question has no answer because the coordinate system itself ends there. Time began at the Big Bang, and our current understanding of physics cannot reach beyond that point. We reach a singularity where density and temperature are infinite and our equations fail. In the first infinitesimal fraction of a second, the Planck epoch, the universe was so hot and dense that all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified. As the universe expanded and cooled, these forces separated and matter began to form. By studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang, we can see the universe as it was when it was only 380,000 years old. This ancient light has been traveling through space for billions of years, stretched by the expansion of the universe into the microwave spectrum. It provides a baby photo of our origin, showing the tiny fluctuations in density that would eventually grow into galaxies and stars. One of the most startling discoveries of the 20th century, first observed by Edwin Hubble in 1929, is that the universe is not static, it is expanding. Hubble noticed that light from distant galaxies is redshifted, meaning the wavelengths of light are stretched as the galaxies move away from us. This expansion is not galaxies flying through space, but space itself stretching between them. Imagine dots on a balloon being inflated. As the balloon grows, the distance between the dots increases. In 1998, astronomers made an even more shocking discovery. The expansion of the universe is not slowing down due to gravity as previously thought. It is actually accelerating. This acceleration is driven by a mysterious entity known as dark energy, which appears to fill all of space and exerts a repulsive gravitational effect. Dark energy makes up about 68% of the total energy density of the universe, yet we still do not know what it is. It is the dominant force shaping the future of space-time. As dark energy pushes the universe apart, the gaps between galaxies will grow faster and faster. In the very far reaches of the observable universe, space is expanding so quickly that distant galaxies are receding from us faster than the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. The space between us is simply growing. Their light will never reach us, no matter how long we wait. They are forever lost to our sight, hidden behind a cosmic horizon. This means that we are living in a unique window of time where we can still see the rest of the cosmos. The Big Bang didn't just create time, it set in motion a process that will eventually lead to the isolation of every corner of the universe. We are witnesses to a beginning that is still unfolding. 12. The end of time. Heat death, the Big Rip, and the Great Silence. If the arrow of time is driven by the increase of entropy and the acceleration of dark energy, what is the ultimate fate of the universe? Cosmologists have proposed several scenarios for how the story of time might end. The most likely scenario, based on our current observations of dark energy, is the heat death of the universe, also known as the Big Freeze. In this scenario, the universe continues to expand forever. Billions of years from now, the night sky will darken as other galaxies are pushed beyond our cosmic horizon. Within our own galaxy, the stars will eventually exhaust their nuclear fuel. The last red dwarfs will blink out, leaving only white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will cool. The universe will become increasingly cold, dark, and empty. Eventually, even the black holes will evaporate through a process known as Hawking radiation, a discovery made by Stephen Hawking in 1974. He showed that due to quantum effects near the event horizon, black holes are not entirely black. They emit a faint glow of particles. Over unimaginable timescales, 10 to the power of 100 years, even the most massive black holes will vanish into a final burst of light. At this point, the universe will reach a state of maximum entropy. Every difference in temperature will have equalized, and no more energy will be available to perform work. Time will effectively lose its meaning because nothing will ever happen again. This is the Great Silence, a timeless equilibrium where the universe is a soup of low-energy photons and stray particles, drifting forever in a dark abyss. Other, more violent scenarios have been proposed. If dark energy becomes even stronger over time, a theory called phantom energy, it could lead to the Big Rip. In this version, the expansion of space becomes so fast that it overcomes the forces holding galaxies, stars, and even atoms together. Everything, from the largest structures to the smallest subatomic particles, would be torn apart by the stretching of space-time itself. Time would end as the very fabric of reality is shredded. Alternatively, if gravity was somehow to overcome dark energy, the universe could reach a point of maximum expansion and begin to contract. This would lead to the Big Crunch, where galaxies fly toward each other, and the universe becomes hotter and denser as it collapses. Eventually, all matter and space would be crushed back into a singularity, perhaps triggering another Big Bang in a cyclical process known as the Big Bounce. These potential endings remind us of the preciousness of the era we inhabit. We live in the stelliferous era, a vibrant, light-filled window in the vast history of the cosmos. We are here at a time when the universe is old enough for complex elements and life to form, but young enough for the sky to be full of stars. We are witnesses to a cosmic drama that has a beginning, a middle, and an eventual end. Time is the canvas upon which this story is written, and our existence is a brief, brilliant spark in the darkness. We are part of a history that is tending toward a quiet, cold conclusion, making the warmth and light of the present all the more extraordinary. 13th. Quantum time. Is the clock grainy? The search for quantum gravity. While Einstein's general relativity describes space-time as a smooth, continuous fabric, like a perfect silk sheet, the world of the very small, governed by quantum mechanics, tells a different story. When we zoom in on the subatomic level, reality becomes grainy, fuzzy, and governed by probability rather than certainty. This conflict between the smooth geometry of relativity and the discrete, jittery nature of quantum mechanics is the greatest unsolved problem in modern physics. In quantum mechanics, everything is quantized, meaning it comes in discrete packets. Light is made of photons, matter is made of atoms and subatomic particles. This leads many physicists to wonder, is time also quantized? Perhaps time doesn't flow like a continuous stream, but moves in tiny, indivisible jumps. Theoretical physicists have calculated a fundamental unit of time known as the Planck time, which is approximately 10 to the power of minus 43 seconds. Below this scale, our current laws of physics, including our concepts of before and after, likely cease to function. Space and time would dissolve into a quantum foam. To resolve the conflict between relativity and quantum mechanics, scientists are searching for a theory of quantum gravity. This is the quest for a theory of everything. One leading candidate is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings exist in a world with 10 or 11 dimensions. In this view, time is just one of many dimensions that emerge from the vibrations of these strings. Another approach is loop quantum gravity, which focuses on the geometry of space itself. It suggests that space is not a vacuum, but a network of discrete loops of gravitational field lines. In this theory, space-time is a spin foam, a granular structure that only appears smooth at large scales. If loop quantum gravity is correct, then there is a smallest possible volume of space and a shortest possible interval of time. Time emerges from the dynamics of these quantum loops. These theories aim to explain what happens at the singularity of a black hole, or at the very first moment of the Big Bang, where Einstein's equations produce infinite results that make no sense. They suggest that at the most fundamental level, time might not even be a basic property of the universe, but an emergent phenomenon, something that arises from more complex, timeless interactions, much like temperature emerges from the motion of molecules. If time is indeed grainy or emergent, it would change everything we think we know about history and causality. It would imply that the flow of time is a macroscopic illusion, a high-level approximation of a much stranger, deeper quantum reality. We are standing on the threshold of a new understanding, peering into a world where the clock of the universe might tick in the most infinitesimal intervals, weaving the tapestry of reality, frame by frame. 14th, the paradoxes of time travel, grandfathers, wormholes, and loops. The flexibility of time revealed by relativity naturally leads to the most fascinating question in all of science. Can we travel through it? Travel into the future is a proven reality. By moving fast or living near a strong gravitational source, you can reach the future of those you left behind. We are all time travelers into the future. Some of us just go a little faster than others. Travel into the past, however, is far more problematic. It introduces logical contradictions, like the grandfather paradox. If you went back and prevented your grandfather from meeting your grandmother, you would never be born, meaning you couldn't have gone back in the first place. This creates a loop of non-existence that the universe's logic cannot resolve. To prevent such logical disasters, Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics always act to prevent the formation of paths into the past. However, Einstein's equations do mathematically allow for such paths, such as wormholes, tunnels through space-time that could connect two distant points in time. If one end of a wormhole was accelerated to near light speed, the two ends would have different times, potentially allowing someone to step through into their own past. Another theoretical solution was found by the mathematician Kurt Gödel in 1949. He showed that in a universe that is rotating, space-time could curve so severely that it forms closed, time-like curves. In Gödel's universe, you could travel in a circle and end up at the moment you started. While these solutions are mathematically valid, they require exotic matter with negative energy, which we have never seen. Most physicists believe that a final theory of quantum gravity will rule out backward time travel to preserve the logical consistency of the universe. For now, the past remains a land we can only visit through our memories and the light of distant stars. Our journey is strictly one way, always forward into the mystery of tomorrow. 15. The Cosmic Legacy. We are stardust and time. We often feel small when contemplating the vastness of space and time. But the story of time is the story of us. We are not separate from the cosmos. We are the cosmos experiencing itself. The iron in your blood, the oxygen you breathe, and the carbon in your cells were not created in the Big Bang. They were forged in the nuclear furnaces of ancient stars. When those stars exploded as supernovae, they scattered their enriched material across the void. That material eventually coalesced into our sun, our Earth, and ultimately you. You are literally made of stardust. Time is the medium of this incredible journey. Your existence is the culmination of 13.8 billion years of cosmic evolution. This realization should be empowering. You are the inheritor of a cosmic legacy. Through your eyes, the universe sees its own light. Through your mind, it contemplates its own laws. We are the ones who turn duration into experience. Every moment of your life is a unique event in the fabric of space-time, eternal and unchanging in the eyes of physics. You are part of an unbroken chain of causality that stretches across the eons. We are stardust, we are time, and we are home. 16. The final reflection. Resting in the flow. As our exploration of the fourth dimension comes to a close, take a moment to reflect on your own journey. You are a time traveler, moving steadily into the unknown future at a rate of exactly 1 second per second. Your trajectory through space-time is unique, a personal path through the vast, curved fabric of the universe. As you drift towards sleep, imagine yourself floating on that eternal river of time. Feel the connection between the rhythm of your breath and the expansion of the galaxies. The universe continues its grand, silent dance. Somewhere in the dark, a star is being born. Somewhere else, a black hole is evaporating. The cosmos is expanding, and time keeps its steady, inevitable pace. Close your eyes. Let the distractions of the day dissolve into the silence of the night. Allow the currents of space-time to carry you into the quiet sanctuary of rest. You are a part of this fabric, a thread in the tapestry of existence. The future will arrive in its own time, and it will be as mysterious and beautiful as the past. For now, there is only the peaceful and gentle flow of this moment. Good night.